It's my pleasure to introduce Professor Yoel Fink from MIT. Fortunately, he has a long bio full of awards, so I'm just going to summarize. And he's a professor in the Material Science and Engineering Department at MIT. And he received his, he has 2 undergraduate degrees in physics and chemistry from the Technion in Israel, and then a PhD from MIT that he received in 2000, when he immediately became an assistant professor in the Materials Department at MIT. So he was, if I may just summarize the prizes, he was a recipient of the Technology Review Award for the 100 Top Young Innovators, which I think is remarkable, in 1999, and was also awarded the National Academy of Science Initiatives in Research Award for 2004. He also has several teaching awards, which I think is also remarkable. And he is a co-founder of OmniGuide Inc. It's a company that I hope he will tell us what they do.
Yeah, I definitely will. Well, thank you very much. Thank you very much. And guys and gals, thank you very much for joining us here today. And I know at my school, we're not allowed to teach between 4 and 6 to allow for physical education. And so people, but it is a great pleasure to be here in this beautiful town. So I'm going to talk to you today, tell you about a new class of materials that we've been working on in the past few years. These are multimaterial, multi-scale fibers. And there's a number of different themes in my talk, but one of them is really to show how these types of materials and the processing approaches that we've developed actually allow you to bridge divide, which is between the macroscopic world and some of the nanostructures that are so elusive. But before we get started, I'd like to remind you all that one area in technology that has been very successful in imparting function and functionality has been that of semiconductor devices. So here's an example of a transistor. And if you think about a transistor, there are 3 dimensions I'd like you to be thinking about. The first dimension actually has to do with different materials. Obviously, to achieve or to realize a transistor, you need 3 different types of materials: metals, semiconductors, and insulators. The second is the geometry. These materials need to be arranged in a very specific orientation, a very specific geometry, get the right interfaces and the right interface quality. And number 3, which is probably the most difficult to achieve, is to get the length scales down. Obviously, the gate dielectrics and oxides are down to 10 plus nanometers. And once you're able to do that, well, you could pack many of these devices and use these for logic, for detection, and so on. And we all know at this point that all of these, satisfying all these requirements, comes at a cost. And the cost is associated with the fact that you're really taking a wafer and taking it through a series, many steps, batch processes. You basically have a small wafer to begin with, rigid, it needs to be packaged, and it's difficult to integrate different types of functions. On the other end of the spectrum are optical fibers. And what's interesting about fibers, when you compare them to the semiconductor devices in those 3 dimensions that we talked about, from a material standpoint, optical fibers are made primarily of insulators, silica. In terms of geometries, these are usually cylindrically symmetric, core clad. The feature sizes here are defined by the core size, the core diameter, which for single mode fiber is about 10 microns. So you could already compare and contrast what makes a semiconductor device so different from an optical fiber. But optical fibers are very interesting because they are made in a very scalable, simple way. Why? Because an optical fiber actually starts with a large object. And what you then do is you heat it up and draw it down. And in doing so, you actually generate many tens of kilometers of material. So it's all about asking the right questions. And so really, a few years ago, we started thinking about whether we could achieve the necessary conditions for really getting these types of devices, yet use the types of scalable processes that are being used for optical fibers. And this is where this whole idea of multimaterial fibers came up. And in the past few years, we've been able to show that many of the necessary conditions on achieving functionality in semiconductor devices could be achieved in a fiber. Here's an example of a preform, a large object that has in it semiconductors and metals and encapsulated in an insulator that you could then draw them down and basically achieve the geometries, the length scales, and the very small features with a processing approach which is very interesting and compelling, and obviously it's being drawn from the fluid state, we'll discuss. And so this brings us to something which is really, at this point, somewhat of a vision, a long-term prospect. And it really goes to a question of how sophisticated could a fiber become. And we think about the fact that the clothes that we're wearing are actually made of thousands, if not millions, of fibers. And these fibers, by and large, are designed to impart thermal insulation and obviously to take on coloring, have a particular color, so for aesthetic purposes. But could we imagine a world where our fibers actually take on a much higher level of functionality? What would it really take to realize that, that dream, that vision? Well, one would have to build into fibers multiple devices. Here's an example of a cross-section of a fiber, which has 8 different devices. I'm going to talk about what these fibers can do. Now, in a world in which a fiber becomes a collection of devices, and then the question is, how many devices could you build in? Is 8 the maximum? Could you do 100? Could you do 1,000? Could you do more than that? Okay, so that's one question, is how functional, how complex could a single fiber become? And then there's a question of, well, what happens when you combine fibers into something that we sometimes refer to as a fabric, and what system level problems or challenges or opportunities would then manifest themselves? And so what I'm going to be talking to you about is sort of the genesis of this whole project, and how we started with making fibers for transmission purposes, and then realized that really the process of drawing fibers is about generating surface, and if you have surface, well, and if you could functionalize that surface, then interesting opportunities would come out, and then we'll talk about different structures, and then how we started drawing metals and making semiconductor devices. So this all started with a question which we were thinking about while I was a graduate student, which was, how can we define really the most efficient reflector possible? And at the time I was thinking about, we were imagining 3-dimensional photonic crystals and imagining dielectric structures that have complete photonic band gaps. And back then, and even now, it's pretty difficult to realize these structures on large areas. And so I was trying to figure out ways to get around some of the fabrication limitations associated with 3-dimensional photonic band gap structures. So going back to the basics, there are a number of different types or classes of reflectors that we know of. One is based on just metals. And these tend to be omnidirectional in their reflection, but obviously have losses due to finite conductivity. Another type of reflector that is used in laser mirrors, for example, is that of a dielectric mirror. Here we're using one-dimensional periodic structures. And these tend to be very efficient at particular angles and angular ranges, but leak light, for example, in Brewster angle. And so I was wondering if one could actually get the best of both worlds and design a mirror that would really bring us as close as possible to being the most efficient mirror possible, under a constraint that really these mirrors had to be simply fabricated. And at the time, we figured out that, in fact, a one-dimensional periodic structure, while not having a complete photonic band gap, could still exhibit omnidirectional reflectivity, provided that the source of the light is actually in an ambient medium. And in order to achieve this omnidirectional reflectivity from a dielectric structure, one needed to generate a photonic band diagram that look like this. So this is the frequency, this is the parallel wave vector, this is the component of the wave vector that is conserved in the z direction. This is the direction of translational symmetry. And basically, one could differentiate between a TE polarization and a TM. And what you see here are the solutions in blue, are propagating solutions of the infinite crystal, if we were to create one. These solutions actually are propagating in the crystal, and between the two propagating bands there actually is a range of frequency for which there's no propagating solutions. However, what you could always and immediately realize is that regardless of any frequency you choose, at some k vector, you always couple to a propagating solution. And this was the reason why, at least at the time, people thought that this type of structure could not reflect omnidirectional. The realization that we had was quite simple, and really what we said is, provided that your source of your excitation or light came from an ambient medium, and provided that we're looking at solutions which could propagate through an ambient medium, well then we need to only consider that portion in phase space that lies above the light line. And if we could design a crystal for which in this restricted area in phase space there are no propagating solutions, this region over here, well, this region would be that of omnidirectional reflectivity, because light that is traveling at k z equals 0 means light has come over here, and this is coming perpendicular to the surface, is in the band gap, and all the way for both the TE and TM polarizations, all the way up to the light line, in which light is actually traveling in this direction only. And so for this restricted problem, in which light is actually emanating from an ambient low refractive index medium, you could define what is an omnidirectional reflector. So this gave us a good place to start. And at the time, we started thinking about, well, here's a surface that reflects light efficiently. It could reflect light from all angles. How about making a waveguide out of it? And turns out the waveguide, this type of waveguide would have some interesting properties. In particular, you could differentiate between 4 types of solutions in this type of structure. So first of all, there would be core-guided modes. These are modes which are propagating in the core. This is the direction, the z coordinate, and evanescently decaying into the structure. These are essentially the modes here in pink. They lie within the band gap of this periodic structure and above the light line. That means they're propagating in air, they're above the light line, they're within the band gap, so they actually don't leak out. They're evanescently decaying into the structure. A second type of mode would actually be propagating only in the structure and decaying in the air. These would be modes that would be below the light line, meaning they decay in the air, and because they're propagating modes of the crystal, they could actually exist in the crystal, and you could convince yourself that they're surface states in which you're in the band gap and below the light line, so you decay both into the crystal and into air, and also just radiation modes which are not confined. So not going too deeply into it, the analysis of the mode structure in this cylindrically symmetric structure, which has this one-dimensional periodic structure in the radial direction. Actually, the modes in this structure are reminiscent of a mode in a hollow metal waveguide, which were studied many years ago. Actually, were discovered by Southworth in the 1930s. And in fact, it turns out that while not having obviously purely metallic boundary conditions here, the modes in this structure, in fact, are reminiscent of the modes in a hollow metal waveguide, with some important differences. One of them is in the hollow metal waveguide, there's a pure separation in TE, transverse electric and transverse magnetic modes. That does not exist in the dielectric structure unless it really is an angular momentum 0 type of mode, in which you actually get this very clear separation. Angular momentum 1 modes, and obviously angular momentum is a good quantum number here because of the cylindrical symmetry, actually give you mixed modes that have both the TM and TE nature to them. And basically the point of this graph is to say the modes here that we're looking at These are the metallic modes. The ones in bold here are the modes that actually exist in the dielectric structure. And the point we're trying to make here is they're actually pretty similar and have some interesting and important differences. So the idea here was quite simple. Up to this point, fibers were always limited by the losses of the material the fibers were made of. You could never make a fiber that is more transparent than the materials that's made of. Why? Because light had to go through a fiber. However, if you could use this mechanism for confining light, light could actually go through a hollow core, and you would then suffer or have losses that are much lower than the intrinsic material losses. So these were calculations in which we showed that you could actually have a fiber that has much lower transmission losses than its constituent materials. The reason that was important is because for many years, since the advent of fibers, you were really stuck with a very small set of materials that could be made into fibers anyway, that had sufficient transparency, and silica was obviously the most important one. But silica, even though it's transparent, it's only transparent in certain wavelengths, and obviously above 2 microns, it's not very good. So this was the idea, and so then we set out to develop and make fibers that had this structure, as opposed to the index-guided structure that existed before. And again, the basic idea here was to create fibers that had lower losses than their constituent materials, allowing us to guide light at wavelengths for which there are no transparent materials. Okay, so this is pretty easy, right? What we need to do is we need to make a fiber that has a hollow core. And remember, for these one-dimensional photonic structures, photonic bandgap structures to work, you need the layers to be a quarter of a wavelength. Quarter of a wavelength in the material needs to still be scaled in physical dimensions by a factor of the index of refraction. And so by the time you're making waveguides for 1 micron radiation, it turns out that your layer thicknesses have to be below 100 nanometers, typically for the types of materials we're using here. And so then the challenge became, well, how in the world are you going to be making fibers that are kilometer length scales with features that are 100 nanometers, sub 100 nanometers, maybe even a micron? People know how to make micron layers on wafers or on substrates, but how are you ever going to do it on the inner part of a fiber? If you think about it, achieving uniformity over a kilometer length scale while controlling features down to well below 100 nanometers gives you a challenge from a processing and fabrication standpoint that is on the order of 10 to the 10. So that was the problem. And what we did was kind of looked at how silica fibers were made and realized that what's really beautiful about the process of making fibers is you start off with the preform. It's a large object. It is exactly a scaled up model of the final fiber, so it has a hollow core, it has a cladding, and it could have the layers inside. And so what we imagined is building one of these preforms out of materials that all flowed at the same temperature. And the hope was, well, we take it, we heat it up, we draw it into a fiber, and that's it. And we don't have to worry about microfabrication, nanofabrication. Okay. So came up with a process, identified materials that could flow together. We're using high glass transition polymers together with semiconductor glasses, kind of make a preform, draw it on a draw tower, and basically this is what we got. And obviously there's a good reason for showing this, because I'm always, how would I say it, as a student I always remember watching all these talks and they present the problem and the solution and hey, it's all pretty straightforward. But in real life things actually look like this. And in particular, as you're starting to kind of realize this approach, lots of things could and did in fact happen. And let's talk about some of them just briefly. One of them is you have this hollow core, and the hollow core is compressible. And obviously as you're drawing this thing down, that surface area associated with the hollow core is increasing. And one of the things this hollow core would love to do, being in a fluid state, is actually to collapse, because that would minimize the surface area and the surface tension. Another thing is we actually started with taking polymer sheets and coating them with this semiconductor glass and then wrapping those around, Well, as you wrap them around and then draw this thing, there's lots of little gases that get trapped, and once you heat them up in the draw tower, they like to bubble up and form these very nice little inclusions here. But the take-home message from all of this was, at least there was some good things that were going on. For example, the fact that the materials appear to be flowing at the same temperature, which at the time we thought was nice. And then we got a little better at this, and at least we could maintain a core, but this is a very large, the layers here are about 20 microns or 30 microns, and this could work for some very long terahertz waves. And then eventually one focuses and goes through an iterative process and studies all the failure modes and realizes that gas has to be evacuated and consolidation has to happen, and you have to actually dry out the polymer sheets very well, and so on and so forth. And eventually you reach these types of structures over here. And this is what a fiber looks like today. So you see the hollow core over here, and where's the pointer at? It's hidden. Thank you. So you see there's a hollow core here, and this ring over here, when taken up to large magnification, high magnification, you can see has many layers. This is a 250 nanometer, so each layer here actually is less than 100 nanometers. And the nice thing here is that these fibers guide light by virtue of the structure. So it's not that the materials are transparent or anything, actually they're highly lossy, but it is getting the period right that gets you this very rapid evanescent decay. Obviously we're using here materials that have very large index contrast, and that defines a large potential here. And then you could scale the layer thicknesses down as you're making these fibers by drawing it down, and your fiber goes from transmitting at 10 microns to 1.5 to 750 and even to the UV. So this was the first demonstration. And let's talk about some of the things that could go wrong and not spend too much time on this, but at least I'd like to give you an appreciation for some of the subtleties associated with this process. So let's suppose we started with a thin layer of a material that is encapsulated in, let's call it a matrix. Okay? And let's imagine this thin layer is made of a metal. Metals, as we know, are crystalline, and crystalline materials, when you heat them up, they melt, and they go from very high viscosity to very low viscosity. And then you kind of draw this into a fiber, and you say, perfect. Here's my layer of metal that I have now in the bottom of it, and I should just have a fiber with a nice little sheet of metal inside. And in fact, as we launched into this project, we just took a picture of the preform and said, this is the dumb deal. Well, it turns out that when you examine the preform, it does not have a layer in it at all, but it has these very fine cylinders going through it. And these fine cylinders are coming about because of a process which is not that different from a capillary breakup process, which happens when you take a little tea kettle and you pour it from some height. This is a little Moroccan restaurant in Charleston near from where we are. And you can see that obviously the T cylinder is breaking into spheres. In this case, there's a layer that actually is breaking into the cylinders. It's a two-dimensional version of this. And it actually turns out that you could get this kind of breakup or not get it at all. And it really depends on a number of things here. So here's an example of a cross-section of a fiber. See a cross-section of a fiber. And it's the semiconductor here we're using is selenium. And you can see in certain cases the selenium maintains its layer thickness. And then as you actually get deeper and deeper into the fiber, this is in the radial direction, you see it begins to break up. And here it's breaking up actually to very small cylinders. On the other hand, if you were to use a different amorphous semiconductor, arsenic triselenide, you find that even actually going down to very, very thin layers, you actually maintain it. And this has to do with the time scales associated with the breakup, which go like the feature size and scale inversely as the viscosity. Selenium actually is a very low viscosity material when it heats up, and actually the time scales for breakup turn out to be very short, and there's been a number of papers on this topic. Let's talk about what good can these fibers do in the world. Okay. This plot here shows the absorption coefficient in inverse centimeters of light, electromagnetic radiation, in water. Okay. And what you can see here is that the absorption coefficient associated, and this is a log scale, absorption coefficient associated with radiation that is below 1 micron is very, very low. In fact, green light at 532 could penetrate through significant lengths of water. And as you go into the infrared, this absorption coefficient climbs by many orders of magnitude. And around the CO2 wavelength, it actually turns out to be, the penetration depth is on the order of 1 wavelength in microns. Why is that interesting? Imagine yourself now a surgeon. You're a surgeon. And what you'd really like to do is cut very precise. So what do? You take a scalpel. Now what does a scalpel do? You're taking force, and that force is distributed over the area of that blade, and it translates into pressure, and that pressure interacts with the surface of the tissue, and you cut through. Imagine now that you're trying to operate on the internal parts of a patient, and you're trying to do it minimally invasive. So you don't want to open the patient. How do you get your scalpel in there? Well, that's pretty easy. I'll just use a light. I'll use light as my scalpel. I'll use an optical fiber. I'll just send power in, and I'll bend it around the corners and just go and operate wherever I want. This plot here defines why cutting with light is very imprecise. And the reason is right over here. This is the window of transparency of silica fibers. And what you can see here is in this window, light actually goes through significant lengths of water. Why is that relevant? Because your tissue is made of water. And so you may be illuminating the surface, but you're actually irradiating volume. So as you're trying to cut internal or inside the body with your green or red or infrared light, what happens is you start increasing the power. Yeah, eventually you start damaging the surface, but in the meantime you're damaging structures that are well internal to the surface you're trying to cut. And so you find that there's enormous collateral damage associated with cutting with light. So this was a major impediment. And what people figured out is that what you really want to do is operate with a wavelength that actually is absorbed very strongly in water. And so the interaction of the radiation with water is very much a surface interaction, similar to what you have with the scalpel. The only problem is that a CO2 laser at 10.6 microns did not have a transparent material, and so what people started using are these line-of-sight lasers. Basically what they do is they aim them from outside of the body, they create a line of sight between the laser. Yeah, this is state-of-the-art minimally invasive surgery. So suppose, don't laugh, because this is what people do. Hopefully not to us, but if you have a lesion or a tumor in your airways, basically what's done is they put in a steel pipe and they illuminate that from outside of the body. That's the way it's done. Now, unfortunately, there are plenty of places in the body you can't really see from outside. And so regardless of how sophisticated you get in your steel pipes, you just can't establish a line of sight. And so this whole way of doing things, while becoming very popular, had its limitations. And so really what has happened with these fibers, which basically here's a little example of the preform of making them, is these fibers are now being used for surgery, and actually every month now about 1,000 of these surgeries are being done. I'll show you just one example of it. Here's this is a CT of a baby, a 9-month-old baby that has a tumor on her spinal cord, and basically what's happening here is a doctor here, Dr. Ellenbogen from Harborview Medical Center in Seattle, his department head, is actually removing a tumor. So this is the tumor that's sitting on this baby's spinal cord. The problem here is actually not access. The problem here is that when you are cutting things on, and this is the spinal cord, so this is the dura surrounding it, when you're cutting through this, there basically are the entire nerve structure, the spinal cord is right underneath here. And if you were to illuminate the spinal cord, you could actually impair its function and create a situation where this baby would not be able to walk again. So what this allows you to do is actually get a very, very precise cut damage only the surface cut through it while minimizing the risk of really damaging underlying structures. Basically what this is mapping to is a much more precise tool for removal of tumors. And one of the areas that this has been adopted is not only in spinal surgery but in cranial surgery. And it turns out that there actually isn't a very precise way of cutting tumors out of the brain these days. And it turns out that in the process of removing a tumor, a meningioma or other types of glioblastomas, other types of cranial tumors, you actually end up removing a whole lot of healthy brain tissue. And one of the attributes of the CO2 is that it really cuts very precisely. This is the thermal damage zone, and it very much abuts the area that is being cut. So it actually allows you to produce very, very precise cuts while minimizing the collateral damage, which is plotted here on the y-axis. So what is being done today? Just to give you a sense of the translation from what they call in medicine the bench to the bedside. There are about 250 hospitals that are using this in the U.S. and now in other places in the world. And as I mentioned, about 250 surgeries per week. About, at this point, 14,000 of these surgeries have been performed. And the area that this is impacting is otology, so operations in the middle ear for recovering hearing. Neurosurgery is one thing we talked about, and removal of airway lesions and airway tumors, head and neck cancer. Okay, so we'll switch gears here and talk now not about transmitting through the length of the fiber, but actually using these fibers as a reflection structure, a structure that is being used to reflect light in very specific ways. We talked about the periodicity and the fact that the periodicity actually introduces band gaps, very similar to the band gap that you would get in a semiconductor. Just obviously the band gaps here are in the photonic band diagram and not in the electronic band diagram. What happens in a semiconductor when you create an imperfection, those imperfections are associated or generate localized states within the band gap, and in fact that same thing would happen here if we created an intentional imperfection in these otherwise periodic structures. We'd actually get within our band gap a localized mode. And this localized mode, the way you'd measure it is actually take a reflection spectra. The band gap would just give you a very broad reflection. This is a reflection coefficient as a function of frequency. So it would give you a very broad reflection. However, once you have a defect in your structure, you get a very sharp transmission line. And that transmission line and the sharpness of that transmission line actually relates to how localized that mode in fact is. So here's an example of fibers that are now, they have a hollow core, but the hollow core doesn't serve any specific purpose. In fact, the entire photonic structure is now on the outer circumference. And again, we go through this process of increasing the magnification. And you can see there's a periodic structure, and then we insert a layer that is off the periodicity. And that layer actually gives you a very sharp transmission line in the otherwise broad reflection band. This is how these materials look. This is work that was published in Optics Letters. This work is being funded by the U.S. Army, and one of the ideas that we had there is actually using these to create fabrics that could be optically identified by just illuminating them with a laser. So now I'm going to start connecting some of these individual pockets of information and trying to create things that are more complex and more functional. We talked about having an annular or cylindrical mirror. Well, here's what happens when you put a gain medium inside. Once you do that, you actually get optical feedback now in the radial direction. And so you then pump this optically, and what you could get is, in fact, lasing action in the radial direction. This is interesting. This is the first fiber that is actually a surface-emitting fiber, a vertical surface-emitting fiber structure. Now, initially, we thought that since the structure itself is cylindrically symmetric and the gain medium inside is isotropic, we should get a wavefront that actually has or shares those same symmetries, namely a cylindrically symmetric wavefront, what we in fact found was this dipole-like wavefront. And that really is a result of the fact of a breaking of the symmetry, and the breaking of the symmetry is associated with the linear polarization associated with the pump light. So if you go from a linear polarized light, in which you get these two lobes emitted in the direction that is perpendicular to the direction of your electrical field, if you go to a circular polarization, you actually recover your cylindrical wavefront, and basically you could use these to create very simple fibers for emitting light or for displays, and by putting in different gain media, you could actually get these to emit in blue, green, and red. And then the next step is to actually not fill it with a solid core, but use a liquid core. And by doing so, you could actually get control over where your fiber is lasing. And so here's the lasing plug, and this is the pump beam, and you actually get a very nice collimated lasing line. And that sort of borders or is a connection between microfluidics and the fluids that are flowing through this very small core, and the fact that you have this optical confinement mechanism. So now I'll talk about some of the ramifications of including a metal. And again, I started off with going with a preform that has this thin metal shell, and having it in fact collect or break up into cylindrical structures. These were not very ordered, but you could get very ordered structures as well. And then realizing that it really is capillary breakup that is driving it. And so initially we designed electrodes that are much closer to their cylindrical equilibrium structure. And so this is how we make them. We actually start off with a semiconductor core. We put a polymer shell on it, insert the electrodes, consolidate it, and then get this drawn into a fiber. And we're able, by doing so, to create fibers that have semiconductor contact with metal and polymers that could be drawn and are very long one-dimensional devices. And when you connect the end of this fiber to a circuit and then illuminate it, basically you get changes in conductivity, photoconductivity. You could detect those changes, and those changes could be used as a simple photoresistor to detect illumination along the entire length of your fiber. So this is basically a sketch of how the fibers are used. These are very long materials. You sit at the edge of them, connect them to a circuit, and when you illuminate the fiber, you could then read the information and get information on whether or not the fiber is illuminated. You could then also put on top of these fibers the fabricated structures, the photonic bandgap structures with a defect, and basically use it to filter specific wavelengths, and use this as a very simple fiber or fabric spectrometer. Now, the problem with these structures or fibers, the good thing is that you could actually detect light along a very long length. Again, this is external illumination that you're detecting. It doesn't give you a good way, a very easy way to actually detect where along the length you're being illuminated. And this, the localization of the waves is actually done by weaving this into a structure. And in fact, if you take two of these structures and put them together, you could create a simple system. And so the circuitry is actually built into the frame here. These individual fibers are photodetectors. You feed this into a computer, and what this computer is capable of doing is detecting not only where the light is hitting one of these screens, but also the vector of propagation. This is a simple mag light, and showing how these structures could actually end up being used. Now, some of the discussions I had before coming into here, I think is an insight that people that develop new materials have, which is it's great to develop new materials, and in particular if these materials were never really done or used before, the biggest question is, so what? And if you think about the world only as a materials developer or a materials designer, and as I mentioned, if you're coming up with new materials, you very quickly run into a question of, so what? And in order for you to really get these materials to the next level and have people really recognize how important they are, you actually need to be imagining what systems one could build in order to make good use of your materials. And so developing systems actually became part of what we in fact do. And so here's an example of how these fibers are then made into a sphere, and this sphere now could detect light from all 4 pi sphere radians, showing what interesting architectures could actually come about when you have these very interesting one-dimensional photodetecting structures. So we're doing these experiments with these grids, and we're imagining that in the future these grids are going to look really like bug screens and are going to be very, very thin, and you could actually propagate light through them very efficiently. And one of the things we immediately realize is that these grids are capable of measuring the direction of propagation. And that was neat. As we said, well, you know, if you think about a lens, what a lens does is an analog computer. And what it does is it, you know, in a very simple geometric optics interpretation, it takes a ray and it maps it to another ray. Well, great. These two grids actually could measure the direction of your incoming ray. And when they connect this up to a computer, you could put a lens transformation, you could put a transfer function there, and basically answer the question of what would happen if you had a lens in your beam. That was the idea. And at least in terms of ray optics interpretation with single rays hitting your screens, this actually works quite well. And obviously the next step was, well, how far could we actually get in digitally emulating the properties of lens? And obviously this got us thinking about reconstructing two-dimensional intensity distributions from parallel projections, and realizing that really what happens in a parallel projection is you have a point source, you have a point detector, and your ray is actually going through this two-dimensional object, and in the end your detector basically picks up an integration of what that beam or what that ray saw as it passed through your entire object. So that number you read off a detector, in the end, is a one-dimensional projection of your two-dimensional images. So you're really looking at an integration process. And if you want to actually reconstruct the two-dimensional distribution, you need to have a large number of these parallel projections. And this is an algorithm that is called back projection, basically at the roots behind the computer axial tomography. And so basically what we did was we started with a very similar process, and realizing that what our fibers are doing is they're not picking up a single point, but if you take a fiber and connect it up to the edge and measure the current, that current is in fact an integration of what this entire cross-section of illumination is exciting within the fiber. And so there is an exact isomorphism here between your parallel projection that was defined based on point detectors of the ray integrating through a two-dimensional distribution, and what a fiber detector would see if it interacts with the two-dimensional distribution. And so in fact one could use the same parallel projection algorithms to infer what a two-dimensional distribution would look like, and basically start off with a series of parallel projections, and basically then use the back projection algorithm to get a two-dimensional intensity distribution. And obviously the next step was to say, well, that's good, but really what we need to get is a sense of the phase. And it probably is not surprising to you that in the far field, most of the information about your object is in fact captured in the phase. And so if you take your far field amplitude and inverse Fourier transform it, you actually don't get anything that resembles your object. But if you take the far field phase distribution and inverse Fourier transform it, you actually get something which begins to resemble your object. And so the next step here was using the fact that we could obtain two-dimensional intensity distributions and putting this into what is a fairly standard phase retrieval algorithm, and basically using our ability to pick up the two-dimensional intensity distributions to calculate the phase, using the phase retrieval, and basically starting off with our two grids here. One needs to rotate them in order to get the two-dimensional intensity distribution. You apply the Fresnel transforms and basically get these to converge. And basically here's our two grids. this is our object over here. We're illuminating it basically with monochromatic illumination, and then we're looking at two planes here. You could call one the Fresnel zone, the other one the Fraunhofer zone, but basically the information coming off these grids is then fed into a phase retrieval algorithm, and then one could actually calculate what the object is, in fact, what it is, and obviously there's no lens in the beam packet. Now, all of this was initially based on the detectors that I just mentioned to you, which were bulk detectors. There's a bulk semiconductor running through the entire core of the fiber contacted by these metals. But then we realized that, in fact, light penetrates to a very shallow extent into the semiconductor, and we would be better off from a standpoint of signal to noise to just going to a very thin semiconductor shell. And that allowed us to come up with a concept of these nested detector shells. And it turns out that if you put one layer of semiconductor with these four metal electrodes, you could get direction of illumination now on a single fiber. If you put two layers, the light that comes out back through these could actually be wavelength discriminated. And if you put three layers, you could actually map your intensity and your light into a color scheme. This is work that was published over the summer in Nano Letters. Basically, we showed here that the design of the fiber with these 8 electrodes actually gives you a tuning curve that allows you to, in fact, measure the wavelength of illumination. And if you have polychromatic illumination at 2 wavelengths, you could actually discern the intensity associated with 2 of these. And if you go back to the Fresnel transform, what you immediately see there is that distance in the Fresnel transform and wavelength actually come about as a product. And so you could either use 2 different planes, or you could actually use 2 different wavelengths. And so here, we took an object and we illuminated it with 2 wavelengths simultaneously, so with polychromatic illumination. We used the fact that our grid is capable of picking up the intensity at these 2 different wavelengths, and obviously use those to differentiate between the so-called Fraunhofer and Fresnel planes. And that gave us the basis for our imaging, now on a single plane basis. Okay, so I'm going to wrap up here. I'm not going to get into a whole lot of details here, but this is one of the projects that is very much now at the forefront of our activities, and it has to do with piezoelectrics and trying to see if we could create fibers that could detect sound, acoustic waves, and trying to use some of the ideas that I just talked about to create fabrics that are capable not only of imaging in the optical domain, but also in the acoustic domain. It actually turns out that the answer is affirmative. These are very, very recent results. This is what these fibers look like. The green here is a result of the fact that there is a Fabry-Perot structure on top of these piezoelectric elements. Anyway, with that, I'd like to end my short presentation for today and mention that really the work here begins with the materials, the geometry, and the length scale. Goes through the integration of many devices, both on a single fiber, on the multiple fiber. We saw a number of different implementations, and there's a whole bunch of applications that we feel are going to, hope are going to come out of this. And finally, I'd like to thank a large number of contributors. These are students and postdocs, and obviously some of the professors I'm working at MIT, John Joannopoulos, Marian Soyich, Stephen Johnson, and a bunch of other people. So thank you very much. If there's any questions, I'd be happy to answer. And thank you very much for hosting me today. Thank you. Questions? Yes?
I got a question about some of the final stuff you were discussing.
Sure, sure.
And how you had this screen that was basically an array of your fibers.
Yep.
And it seemed like, okay, you can increase your sampling density by just
Yeah.
Decreasing the space between the fibers. And I was
That's
wondering
right.
if there are any complications involved with that.
Yeah. So practically speaking, so the answer is yes, there are complications. Now, if I want to map out these complications into various categories, well, one complication has to do with something quite prosaic, which is called connecting to stuff. Okay. you imagine, pull out one of your hairs, okay, and there's your fiber detectors, right? And that hair actually has 15 electrodes in it, okay? So go find, you know actually where they are, but you need to connect up to them in a reproducible way. So part of it is, there isn't at this point, an established paradigm for how to connect up to these things. So what do? We cut it, get the youngest people that could see best and smallest features, and then they actually go dig in and find it. But, if you saw these things, they're 32 by 32, and actually there's a whole bunch of connections that have to be made, which is why we're making the fibers pretty big, okay? So that's one direction. The other one has to do with, if you start making these things, the fibers are large. If you get, there are effects, there may be diffraction just by the form factor of the fiber itself, okay? And so what you actually want to do is create fibers that are very, very, very maybe thin, maybe transparent, and really minimize the cross-section associated with it, so you actually don't get interference between these grids. Finally, the biggest problem is that at this point, in order to get the back projection, you actually need to be looking at your object from a number of different angles. And in fact, if you look at your clothes, there's fibers going here at a bunch of different angles. So you don't really need to move your object as long as you actually have fibers moving in different directions, or arranged in different directions, I should say. This is why it's still in the labs, and we're not running around with clothes that could actually rivaling Nikon's cameras. But the exciting thing is that you could actually create a fabric that has vision capabilities. And while these things could only see maybe 5 or 6 or 7 centimeters out, the answer is it's much further than your shirt can see. So that's can't see very far, but it's a whole lot better than what we have right now. So that's. But anyway, and if you're really interested, obviously the guys to talk to are the students and postdocs that are really doing the work, and I'm sure I'd be happy to educate you about some other dimensions here. Yes?
Can you comment on the mechanical strength?
Mechanical strength, yeah, that's a good one. So the fibers are, the mechanical strength by and large is determined by the majority component. It's a fair assessment. And a majority component is made of these high TG polymers, like polyether imides and polyether sulfones and polycarbonates and polysulfones. So these are actually fairly tough, high tensile strength materials. Now, it is a composite, and you do have rigid elements going through. And so then it becomes a more, once you dig into the next layer of trying to answer this question, I think there's a whole bunch of questions that have to do with mechanical strength. But we're drawing these, and give you an example. The tension that we typically apply, even in the draw, is on the order of a kilogram. Cross-section of a fiber is probably a few hundred microns. And that's when it's in the fluid state. So you actually get fairly high stresses developing, and that's actually the reason you could realize these intricate structures, is because you really are using the stress fields and viscosities to negate surface tension. Yeah.
How long can you draw your fibers out, and what kind of attenuation do you see through?
Yeah. So I'll give you the place where this has really been being explored on I think on a serious level is actually in production runs.
Mm-hmm.
So production run today is maybe 500 meters.
Okay.
Now these are fibers for 10 microns, so they're fairly large in their features. Typically, fibers are used on 1.5 meters. So you actually don't need to, you don't have to really go through the 500 meters, but you need to cut it into sections. Attenuation at 10 microns is on the order of a tenth of a dB per meter.
Wow.
That's a ballpark.
Mm-hmm.
in the end of the day, it turns out that your system attenuation is a lot more into just getting the couplers and the laser quality.
It's a single mode?
Well, not single mode here is that's a very interesting point, because remember, individual modes here, the core sizes are definitely ones that support a multiplicity of modes.
Okay.
But there is differential losses associated with them, right? Because each one of these modes has very different radiation coefficients and absorption coefficients.
Right.
And so you may actually excite a whole bunch of modes, but in fact, the fiber itself is a very strong filter.
Right.
And so,
Okay.
so in fact, they are, the nice thing here is that you could actually operate with a fiber that has a fairly large core, but get an output that is very close to a single mode output.
Okay.
That's one of the tricks here. In an index guided structure, the differential losses between the fundamental and high orders are actually not that large.
For your 10 micron fibers, have you explored applications in industry too?
No, only
Medicine?
Only in medicine, not in material processing, although that's where CO2 lasers are used predominantly in marking and engraving and putting on dates on bottles. Yeah. So, okay.
What effects do you see of bending the fiber
Yeah.
mechanically and?
Yeah, mechanically, so bending losses couple angular momentum plus minus 1. So you definitely, when you bend the fiber, and definitely when you bend it tightly, depending on the core size and the separation K-space between your modes, you're going to get coupling. And if your core size and the separation between modes is smaller than your coupling strength, you're going to start seeing scattering to higher order modes, and you're going to see the effects of those modes in terms of losses. The trick is to actually design a core size that is small enough to be able to handle the types of bends that are present in your problem, and you can do that. But that's the way. That's basically what the way you think about these things is. You start off with saying, I'm going to need 2 centimeter bends. My wavelength is 1 micron, and therefore the maximum core size that I'm going to be able to sustain is so and so. Or otherwise, I'm going to start getting high coupling losses. So I'll also mention to you that we published a paper a few years back in PRL that talks about how do you actually figure out in a unique way what the composition of the modal output is. And that kind of relates to this question of bending losses and bending effects in these types of structures. That's Ofer Shapira wrote that. You guys want to go home? Okay, well, thank you very much.